In this video, we'll look at the integrals of trig functions, and we'll use the table of derivative trig functions that we developed in another video. Here we have a set of trig derivatives that we derived of previous videos, and we're going to focus on sine and cosine. Now remember, if I take the derivative of sine and get cosine, then if I take the integral of cosine, I get sine, right? It's just literally the reverse of it. So the integral of cosine gives me sine. In an indefinite integral, remember we put sine plus c. This is a graph of cosine, the term within the integral. And we can see what happens when we do a definite integral, right? So set an upper and lower limit. So here we're setting the limit at 0 and pi over 2, right? So lower limit 0, upper limit is pi over 2. So we take the integral of cosine, say that's equal to sine, and then we apply our limits. So you first apply your upper limit, right? So sine pi over 2, if you think about your unit circle, that's going to be the positive x-axis. So it's going to give me a y value of 1. And then sine minus, right? Sine 0. Sine 0 is the horizontal x-axis. So that's going to be 0. So that's equal to 1. So this area is a positive 1. So easy check is at least to make sure that the sign in front of your integral is correct, right? So this is positive value. At least that piece of it is correct. If I say from 0 to pi, then everything's the same except for my limits. So sine of pi is negative x-axis on the unit circle, so that will be a y value of 0. So 0 minus 0, this will give me 0. Here's my 0 to pi. There's the integral is equal to 1. The area is equal to 1 here. This one's below the x-axis, so we know that that's going to give me a negative value. That's basically going to mirror that. So they cancel each other out and give me 0. Then we could look at derivative cosine is equal to negative sine. So I can say the integral of sine is going to be negative cosine. And so here is the graph of sine. And then we can do the same thing, right? Apply some limits to it. So if I apply the limit 0 to pi over 2, take the integral of sine, I get negative cosine. So negative cosine with the limits 0 to pi over 2. At pi over 2, that's at 90 degrees. That's positive y-axis. So the x value is equal to 0. So negative quantity 0, the upper limit, minus the lower limit. Cosine of 0 is equal to 1. That's along the a positive x-axis. And so, and you can see it here, right? So it's equal to 1 right there. So that's equal to 1. So this area here is equal to 1. So then if I extend this to 0 to pi, right? 0 to pi over here, I'm going to shade this area as well. So, you know, even without applying the math itself, we can see that it's just going to be mirrored across the pi over 2 x value. And so it's going to be double this. But we can apply the limits, right? 0 to pi. Cosine of pi is negative 1 because that's along the negative x-axis. Cosine of 0, we said earlier, was 1. So negative 1 minus 1 is negative 2. Minus negative 2 is going to give me positive 2. Right? So easily we can take the integrals of sine and cosine, of cosine and sine using the derivative of sine and cosine. Right? We'll do the same thing for these 4 trig functions. To do it for some of the other like specific components, you will see in future videos take some other integral tools that we're not going to focus on in this video. So we can literally do the same thing that we did for both sine and cosine for these here. So I have derivative of tan gives me secant squared, so integral of secant squared gives me tan. Derivative of cosecant gives me negative cosecant cotan, so integral of cosecant cotan gives me negative cosecant, and so forth, right? And then for integral of secant tan gives me secant, integral of cosecant squared will give me negative cotan. right? And so we have the plus c in each of these because these are indefinite integrals. This one's interesting because we'll see some definite integrals that gives us infinite values. And we can see exactly where that infinity term comes from. So let's look at this one first. And let's start by looking at 0 to pi over 2. So from 0 to pi over 2, those are my limits for tangent. Tangent, remember, is sine over cosine. So I have sine over cosine, pi over 2, minus sine over cosine at 0. And here's a graph of 0 to pi over 2 area. And you see the infinity term comes from your upper limit. And we recognize that here, right? So cosine at pi over 2 is equal to 0. If you think about the unit circle, that's the positive y-axis. So x equals 0. And then here, sine of 0 is equal to 0. So this term is 0. So this is equal to infinity. But I can shift this, right? So if I want to give a finite value, I just won't take it all the way to pi over 2. Instead, I can take it over pi over 4. So again, tangent, sine pi over 4. Remember, pi over 4 is a 45-degree angle. So that's your isosceles right triangle. So I got 1, 1, square root of 2 for the hypotenuse. So sine pi over 4 over cosine pi over 4. Each of these are going to be exactly the same if you take a look at one of the trig videos. So this will give us a ratio that's equal to 1. Tangent of pi over 4 is always equal to 1 because you're looking at the isosceles triangle sides, or the equal sides. Then tangent of 0 we saw earlier was equal to 0, so we get 1 minus 0 will give us 1, right? So then the area is shifted, and it's not going all the way to pi over 2, so it gives us a finite positive 1 value. We could take a look, same thing here. Go start from 0 to pi over 2. We see that we have an infinite area again. This time it's coming from your lower limit, right? So cosecant, remember cosecant is 1 over sine, so I get negative the quantity of 1 over sine pi over 2. Sine pi over 2 is equal to 1, so that's why this upper limit gives me 1 here. Minus 1 over sine at 0. 0 is the positive x-axis, so sine of 0 is equal to 0. Y value is 0 there. So that gives me 1 over that 0 gives me infinite value. So this gives me a positive infinity term as we recognize here. So I can shift the lower limit. So I'll switch this to pi over 2 to pi over 4 to pi over 2, right? Pi over 4 to pi over 2. And then I have the same upper limit 1. Now my lower limit is 1 over sine pi over 4. Sine pi over 4, again, remember it's a 45-degree right triangle. It will be 1 over square root 2, because it's 1, 1 square root 2. So 1 over square root 2 is basically square root 2. So subtract the whole quantity. This is basically square root 2 minus 1. And so that's approximately 0.4. Okay. Let's do the same thing for secant tan. So secant tan gives me secant, so that's 1 over cosine. So from 0 to pi over 2, we get infinity again, right? And this time it's the upper limit that gives me infinite term, which is recognized right there. So 1 over cosine pi over 2, the upper limit, cosine pi over 2 gives me 0, so 1 over 0 is positive infinity, minus 1 over cosine 0. Cosine 0 is equal to 1, so infinity minus 1 is just infinity. So if I want to shift this to a finite value, I can change the upper limit, right? Just back it off and move it to pi over 4, just like we did up here. So if I do that, I got 1 over cosine pi over 4. So that's the same thing as sine pi over 4, right? We'll get this term here basically. So 1 over square root 2, which is basically square root 2. So square root 2 minus 1, like we saw before, gives me 0.414. You can see that this integral term and this integral term look fairly similar. It's just a phase shift. And so we can recognize that there. We can also recognize that in the secant cosecant phase shift piece. All right, lastly, we have cosecant squared. Integral cosecant squared gives us cotan or negative cotan. So from 0 to pi over 2, we'll go for the upper limit, cosine pi over 2 over sine pi over 2. Sine pi over 2 is 1. Cosine pi over 2 is 0. So that upper limit gives me 0. cosine 0 over sine 0, right? Cotangent is 1 over tangent, right? So it's just going to be the reciprocal. So that's why it's cosine over sine. So cosine 0 is 1, sine 0 is 0. So that gives me my infinity term, right? So negative infinity gives me positive infinity. We see in our graph here, the lower limit gives me my infinite term. So I can shift this and say pi over 4 to pi over 2. So we said earlier that my upper limit was going to give me 0. My lower limit, cosine pi over 4 over sine pi over 4. This is the, again, isosceles right triangle. So those two sides are the same. So it's going to give me 1. Cosine and sine at pi over 4 are the same. So I got 1. So negative 0 minus 1 gives me positive 1, as we recognize here. Right? So this is just a demonstration of what the trig functions that we derive from a derivative standpoint can be applied in for integrals just by using that definition that it's the reverse essentially, right? So we could take a look at more advanced tools to take the integral of something like the tangent, which we have not done, right? We took the integral of secant squared that gave us tangent, but we have not taken the integral of tangent. So the result of that, or like cosecant, gives us a pretty different function, and we would need to use some substitution rules and trig functions to help us solve for those, but we can do that in a future video.